Yes, thank you, Mark, for a really nice introduction. Welcome all, welcome to this presentation on the problem of ill conditioning. And today I'm going to talk about the limitations of state-of-the-art torque control strategies for wind turbines. So in the next 15 minutes, I'll be talking about, the next 15 minutes will more or less be a wake-up call for all our control engineers who are developing torque control strategies and who are using torque control strategies in wind turbines. Before I start, I want to give a shout out to the team and the paper that we made as a collaborative effort. And the first and foremost author of this paper is Livia Brandetti, who is a PhD candidate in our group, and she's doing work on digital twins for vertical axis wind turbines. Furthermore, we have Yi Chao, who was a former postdoc in our group but now working at EPRI. And of course, Jan-Willem van Wingerden, who's a full professor and the leader of our wind energy group. And as a team effort, we made this paper on the ill conditioning of the combined wind speed estimator and tip speed ratio track and control scheme. So if you want, I'm going to talk about this paper, of course, in this presentation. But if you want to read the full paper and see the full derivations of all the exciting stuff we did in this paper, just give me or Livia a ring. Then I can send you a preprint. So before I start the whole story, I want to make some assumptions. So this is the only slide in which I use bullet points because I think bullet points are generally not that exciting in presentations. But nevertheless, the following quantities are assumed to be perfectly known. So we have the rotor radius R and the area of the rotor. We have the air density and the drivetrain inertia. These are quantities which we assume, okay, these are in our real wind turbine, and we also assume that these are perfectly known in our wind turbine model. Then we use a wind speed estimator. It's based on the INI estimator, which is originally described by a paper of Ortega. You can see that at the bottom of the screen, and later extended by Yi Chao, who was the former postdoc in our group. And we use this wind speed estimator. We use this wind speed estimate to make an estimate of the tip speed ratio. And we use the estimated wind speed for this and the actual measured rotor speed. Furthermore, we assume that we have uncertain power coefficient information. We assume a direct drive wind turbine with a given ratio of 1, and the drivetrain is assumed to be 100% efficient. So let's first review the general control structures that we normally use. So the K omega squared. So first start with the K omega squared. What you see in the the top right of the screen is our wind turbine, which is of course subject to an effective wind speed V. It has an input, a generated torque input TG, and an output rotor or generator speed, doesn't matter in this case, omega R. We take this measured omega R, we feed that into a controller, square it, multiply it with a certain gain K, the optimal mode gain is mostly used, and then that results in our torque input. And this controller type controls our wind turbine in region to operate at the optimal tip speed ratio. There are of course advantages and disadvantages of this control framework. It's effective, easy to understand, and simple to implement, but there are also disadvantages. So it's highly dependent on prior information. And what do I mean with that? We have this CP curve, which we use a lot. And we use the CP curve information here to determine what the value of K should be. So we use the tip speed ratio that corresponds to the maximum value of the CP curve. And we also use the maximum value of the CP curve in the computation of this K, of this optimal mode K. As a result, we have a predetermined control bandwidth in the blow rate operate region, although it's a little bit varying in the blow rate region. And as a consequence, this control structure is really inflexible in the terms that you cannot tune anything. You just compute the K, you put in your generated torque or your generated torque, your rotor speed, and then you end up using a static function, so nothing dynamic is going on in the controller, in the static function to end up with your generated torque, TG. So that's why we generally move to a more dynamic torque control structure, which makes use of a wind speed estimate to do tip speed ratio tracking. So what you see in the bottom of the screen is again the real system subject to a wind speed V, a torque input TG, and then a rotor speed output omega r. Then we use the inputs and outputs of the system in an observer-like estimator. So this is our estimator, which makes an estimate of our effective wind speed that our wind turbine is subjected to. And using this wind speed estimate, we can also compute the tip speed ratio estimate. This tip speed ratio estimate is, of course, fed to our controller. We have a lambda star, which is our the set point for of our controller, and we want to track that set point as well as possible. Of course, advantages and disadvantages. Now we have a real dynamic controller because there's dynamics in the estimator and also in the controller. It's tunable. We can both tune the blue and the green blocks. And possibly we can get better performance, dependent, of course, on the tuning and the quality of our models, which are inside these controllers, estimators. Disadvantages are complicated to tune and implement. It might be complicated. And it still relies on prior information in the controller and the estimator. And I'll come back to that a little bit later. So let's dive a little bit into more detail what is inside this controller and this estimator. So the estimator effectively wants to make an estimate of your effective wind speed, so V hat. With this V hat and the measured rotor speed, we can make an estimate of the estimated tip speed ratio, lambda hat, and then having some nonlinear model inside of our estimate of our real system, we can make an estimate of our estimated aerodynamic rotor torque. And then what we do, we close the loop, we have some integrators, we have a PI controller, and we use some variables or some signals from the real system, so the generated torque and the rotor speed, to eventually close the loop and end up with this V hat, this estimated effective rotor speed. Then what we do, we take out of this loop, we take out the lambda hat, so the estimated tip speed ratio. We compare that to the reference value, lambda star, which is mostly taken as the top or the maximum value of the CP curve, the corresponding tip speed ratio to the maximum CP value. We compare that in each time step, and we try to integrate away this error at all times. But what's now striking, or what's now interesting to see, is that still, like in the K-omega case, we are really relying on the quality of the CP curve. So the CP curve is contained in the estimator. So this full table just lives in our estimator, and we also take lambda star as the maximum value of the CP curve, which is also just prior information. So in this scheme, we are even more dependent on, it seems like at least, we are even more dependent on the quality of the CP information. So this curve, this is a main topic. So this CP curve is the main topic here. And the main question I'm going to treat in the rest of this presentation is, what if the CP information is inaccurate? What influence does that have on the total control total control structure that we proposed? So let's have a look on a signal basis what this means. So let's say, now you see a red circle on the slide. Let's say that our CP information is inaccurate. What then is again striking to see, of course, but what I think is striking is that this lambda star is a fixed value, or mostly it's taken as a fixed value. And regardless of the uncertainty in CP that is contained here in the estimator, we always integrate away this error. So what this means is that lambda hat is always equal to lambda star in the limit, of course, regardless of the information that is contained, or regardless of the inaccuracy of CP here. So then we move to this block, and what we then see is that if lambda hat here is always equal regardless of the uncertainty in CP, then the ratio between omega r and v is should always also be equal. Only the magnitude maybe varies. So maybe when there is some uncertainty in CP here, maybe then our v is biased. And as a consequence, our omega r is also operating at another operating point. And that might lead to suboptimal operation of the real wind turbine, which we are not aware of. And I'll illustrate it a little bit more in the next slide. So to formalize this problem of ill conditioning a bit, I'm going to do a really simple mathematical derivation. And then you can see really where this ill conditioning comes from. And I start here with a really simple wind turbine model. So you have the J omega r dot is the difference between aerodynamic torque and generated. We consider the steady state case. So omega r dot is 0. So what we then end up with is that the rotor power PR is equal to the generator power VG. Of course, all in steady state. What is now the conclusion that we can draw now is that we always in our estimator have an unbiased estimate of the real aerodynamic rotor torque. And we could see that already in this figure, because we integrate away this error here, and then we always have an unbiased estimate of the real rotor torque. And I think this is a critical observation, and that's great, of course. We can make an unbiased estimate of the rotor torque, but of course there's a catch. And if we now just evaluate this assumption here, so TR is equal to TR hat, then you end up with this equation, which you see on the right-hand side. We made some assumptions. So rho is known, A is known, the half is of course known. So we cross that away. And then we see this relation appear. So what you see here on the left-hand side, you have a product, V cubed times CP, V cubed times CP, which corresponds to our real wind turbine. We do not know both quantities. We do not know what the real wind speed is. We do not know what the real characteristics of the wind turbine is. But we know the right-hand side because these are contained in our estimate. We know V, we know our estimated wind speed, and we also know the table that we put into our estimate. So the conclusion that we can draw here is that we can perfectly estimate the product between V cubed and CP, because these things need to be equal to each other, but we cannot make an unbiased estimate of the individual quantities. So we cannot, under model uncertainty, for example, say, okay, I know for certain that my estimate of V hat is unbiased if there is some model uncertainty in CP hat. And I'm going to show why that is right now. So let's assume that we have defined CP hat as a constant factor times the real CP. This inevitably results in the following. So we still have our left-hand side, which remains unchanged. But if there is some multiplication factor times the real CP, then we have to compensate for that in our estimated wind speed. So as a conclusion, what I can say again, we can always estimate the product between V cubed and CP, but we cannot make a unique estimate of the individual quantities. This is the problem of ill conditioning, which we describe in the paper that Olivia submitted to Torque. So if you want to know more about that and more in depth, please reach out. And what we also do in this paper is that we do a frequency domain analysis. So here you have this whole block diagram, and we completely linearize this whole block diagram, and then just look at transfers from certain quantities to certain outputs. So what we did is that we took lambda star here as an input, and we looked at the output, looked at the real lambda output. So from lambda star to the real tip speed ratio of the tube. And then again, we also looked at the transfer from the set point lambda star to the estimated lambda, so to lambda hat. And for the control engineers, this is of course all closed loop. So this is the complementary sensitivity functions, which we are going to evaluate. So first, I'm going to look at the transfer between lambda star and lambda hat in the left box. And then you get this Bode plot. And I'll first introduce all the lines that you see here. So the black line is with no model uncertainty. The red line is with 0.8 times the real CP curve is taken as CP hat. So 0.8 times CP is CP hat. That's the red line. And for a value of 1.2 uncertainty is the orange line. And we're going to focus a little bit on the low frequency range here that you see in the zoom in plot. So this is just a zoom in of the first part of this plot. And what is funny to see here is that regardless of the model uncertainty that we have in our estimator, the transfer between the set point and the estimated tip speed ratio is always 0 or is always 1. 0 dB is a magnitude of 1. So what we can conclude from this is that the controller always believes it's doing the right thing. So it's always thinking, no matter what the uncertainty is, it's always thinking, okay, I'm doing great. I'm tracking the tip speed ratio you request me, and that's and I'm doing a great job. On the other hand, if you now look at the transfer from the lambda star, so the tip speed ratio set point to the actual tip speed ratio, then we see completely different behavior. Again, we zoom in here, and then when there's no model uncertainty, we still have that transfer of a magnitude of 1, 0 dB. But if there is some model uncertainty into our estimator, then you see that in the low frequency region, you get an offset from the 0 dB line, which means that there is an amplification or a decrease in gain from the set point to the real tip speed ratio, which would mean that we are operating at a different operating point than we originally aimed for. Then, to conclude, some simulation results, because time domain simulations are always also always nice to see. First, for the case of no model uncertainty, so for gammas 1, and in the coming slides, I'll also show it for gamma 0.8 and 1.2. On the left side, you also see the wind speed, so the actual and estimated wind speed. And in the right plot, you always see the tip speed ratio, the actual tip speed ratio of the real wind turbine, and the estimated tip speed ratio. Then for no model uncertainty, everything's perfect. The estimated wind turbine, the estimated wind speed matches the actual wind speed, and the tip speed ratio from the actual wind turbine also matches the estimated tip speed ratio. And you can also see, by the way, the lambda star, so the tip speed ratio set point here in dashed red color. And in average, you see that it nicely fluctuates around this set point. But what now happens if we add uncertainty to the system is that you see that the wind speed estimate is really deviating from the actual effective wind speed. And as a consequence, what we again see is that the controller thinks it is tracking the reference. So the black line is circling or dancing around the red line, the red dotted line here. But the actual wind turbine is operating at a far higher tip speed ratio than what we believe it is. Doing. But because we do not have concise wind speed information, we cannot know what the actual operating point in terms of tip speed ratio is with the actual turbine. Again, same conclusion for uncertainty in the other direction. We now underestimate the wind speed, and the wind turbine is now operating at a lower tip speed ratio than we intended to be. Conclusions, and I subdivided these conclusions into the controller, estimator, and the aerodynamic part. So I already said this a couple of times, but as part of the conclusions, the scheme that I presented always believes it's doing the right thing. No matter what kind of uncertainty you put into your system, it always thinks, okay, I'm following the reference that you asked me to follow. And at the same time, the reference lambda star that we are tracking is also based on information on the CP table that we have to our disposal. So that might also be skewed or incorrect. Then the estimator, there's just not enough information in our scheme or in general, in wind turbines in general, to make a unique and unbiased estimate of the effective wind speed when there wind speed when there is model uncertainty. And I showed that using this relation here. So the product between both quantities always holds, but making a unique estimate of the individual quantities is a problem here. And because of this wind uncertainty, we do not actually know what our wind turbine is doing. So if our internal model of our internal information in our estimators is inaccurate, then we cannot say anything, or in terms of tilt ratio, we cannot say anything what our real wind turbine is doing. So as a conclusion, and maybe a future outlook to coming projects, can we come up with some learning schemes such that our estimated CP more closely represents the real CP or power coefficient characteristics? And it's then, of course, the challenge to only look at signals that are available to us in general in wind turbines. We can, of course, assume that we have LiDAR on top of our turbine, but that's not realistic. So I think it's a challenge for us as researchers and control engineers to come up with schemes that only use the signals that are generally available in wind turbines. And with that, I want to conclude this presentation. Thanks all for listening.
Yeah, great, Sebastiaan. I really enjoyed this talk. I really like how we took a step back and also looked at kind of more fundamental control theory and reintroducing back into our control methods. I think we often miss that in the wind farm control side of things.
Cool. Thanks, Mark.
All right, and with that, I'd like to open up the floor to any questions people may have. Feel free to raise your hand or mute yourself and ask a question. In the meantime, I can ask the first question. Sebastiaan, I saw you did your analysis first with kind of this gamma 0.8 and then of 1.2.
Yeah.
Is this magnitude of error realistic on CP curves, like 20% error? And like, in what situations does the CP curve match well, and in what scenarios does it not match well?
Yeah. So the magnitudes 1.2 and 0.8 are just artificial and just for clear presentation to show the implications if you have to clearly show the implications in the plots I just showed. But it really depends indeed on the type of degradation that you have. So, but you can of course assume that these degradations are really severe in terms of icing. So if you have ice forming on your blades, then you can have a totally different power coefficient curve than when you are in normal operation. You have also other degradation cases. You have, for example, that your wind turbine ages and your blade degrades. So it can be really instantaneous, but it can also be a long-term degradation. And it's still under research what type of CP degradations are really realistic. So what kind of numbers are realistic or what kind of degradation numbers in CP are really realistic? So that's a good question, and that's still under research.
Okay, interesting. Thank you. And then you said something about icing. Do you think having temperature sensors or using those temperature sensors in turbines in your algorithm could help that? Or would you say...
Yeah,
not
maybe for
really.
the I think not really in terms of learning or in terms of correcting the CP table that is in our estimator or controller, but it might be beneficial for detection. So if you for example install microphones or temperature sensors, then you might be able to detect, okay, probably there's some kind of degradation, or probably there's some kind of effect going on in my blades, and now I need to do something about it. But for the active learning part, I do not think that.
Okay, yeah, thank you. Does anyone else have a question for Sebastiaan and Livia? Right, I have actually another question, and it's maybe pulling it back to wind farm control a little bit. Do you think there's any merit to having these turbines communicate with one another while they're learning these CP tables, or do you think these tables are so separate that that's not viable?
Good question. I'm mostly looking at wind turbine control, of course, but I think that each wind turbine should be able to possess accurate CP tables for its own, because what I see in certain papers is that wind turbines in wind farms are used as sensors. So each wind turbine has its own wind speed estimator, and that information is then fused, or sensor fusion, or maybe in a big estimator used in an observer to make a prediction of the whole wind speed in a complete wind farm. But if the wind speed estimation if the estimation of the individual turbines is already inaccurate or biased, then the whole farm, or the whole wind, or maybe the whole wind speed estimation in the whole wind farm might also be incorrect. So I think indeed that we have to start correcting these curves, or start to correct or update these curves in individual wind turbines, and that wind farm control strategies can also benefit.
Yeah, great, exciting. All right, does anyone else have a question for Sebastiaan? Well, it doesn't seem so. All right, then thanks